Good afternoon, participants. That day we have seen that there are a number of hydrological models to study the rainfall or snowmelt runoff. Today we will see how rainfall runoff modeling can be done using the geospatial inputs. So that day also I have shown you this hydrological cycle, and by now you might have understood that most of the hydrological processes can easily be understood using the geospatial inputs, such as for precipitation, direct products of remote sensing based products are available. Similarly, for evapotranspiration, direct products are available. Soil moisture, direct products are available. Now, only we are left with the runoff. How much water will be available, or how much it will be the stream flow in the channels. To estimate that, we cannot get directly from the remote sensing. However, we can model it using certain hydrological models. So you can see here that in the perennial stream you will have the runoff throughout the year, whereas in intermittent you will have runoff only during the season, and whereas in ephemeral streams you will have runoff during these streams, during these storms, during the particular storm. So you can see here, then if your stream is ephemeral stream, you cannot go for the continuous type of models. So again, we have to look at the characteristics of the stream as well to select the hydrological model. Then land use, if you see, then land use also play a critical role in the generation of runoff. So if it is a forest land, the runoff will be less as compared to the bare land or the grassland, where the runoff will be more in the bare land as compared to the grassland, and it will be highest in the urban land because the impervious surfaces and surface in the urban land is more. So there will be less infiltration and more runoff. So if you see, the runoff depends on the rainfall characteristics, such as its magnitude, intensity, distribution in time and space, and its variability. And it also depends upon the catchment characteristics, such as soil, what kind of soil is there in your watershed or basin, what is the vegetation, what are the different vegetations present, what is the topography, what is the geology, shape, and drainage density of your catchment, and then the climatic factors which influence the evapotranspiration. And if you see, the interrelationship between these factors is extremely complex. Therefore, we require a system which is called as hydrological modeling to study the rainfall runoff. So that day also we have seen that what is hydrological modeling. So hydrological modeling is related to the spatial processes of the hydrological cycle and is often used to estimate the basin water resources as well as for the impact of the assessment, or more precisely water resource management. So what is hydrological model? Hydrological model involves the application of mathematical expressions that define the quantitative relationship between inputs and the outputs. So that day we have seen that there are different type of models. So I have told you about the empirical models. So these are some of the empirical models. Those are used in earlier days, such as graphs, tables, and simple analytical solutions to estimate the runoff. So Benny's percentage, as name suggests, Sir Alexander Benny, he has measured the runoff from small catchments near the Nagpur area. The area of the watersheds was around 16 kilometers square, and these watersheds were studied during 1869 to 1872. And then he had developed curves of cumulative runoff against the cumulative rainfall. So simple relationship he has developed, that how much rainfall is occurring and how much percentage of rainfall is the runoff. So two curves were found to be similar. From these, he established percentage of the runoff from the rainfall. So these percentages have been used in Madhya Pradesh and Vidarbha region of Maharashtra for estimation of the runoff yield. So you can see here, simple the rainfall and the runoff relationship has been developed, and based on that, the percentage of the rainfall, how much rainfall percentage will be converted as runoff it has been estimated. And as I have mentioned, the empirical models are site specific. So these this Benny's percentage model can only be applied in the Madhya Pradesh or Vidarbha region, because if you apply these models, the conditions may change, yeah, the characteristics of the watershed and may change in the other region. So it is an empirical approach. Similarly, Burlow's table. Burlow's was the first chief engineer of Hydroelectric Survey of India. So he has studied small catchments of around 130 kilometers square in Uttar Pradesh, and he has developed this kind of relationship between the rainfall and the precipitation, runoff and the precipitation. R is runoff, P is precipitation, and KB is your runoff coefficient, which depends upon the type of the catchment and nature of the rainfall. So this is how he has developed the relationship for the watersheds in Uttar Pradesh. So the Burlow's runoff coefficient KB in percent is given here. If your land use type is like this, or belongs to class A, B, C, D, then you can choose the KB accordingly. And the season 1, 2, 3 are defined as light rain, no heavy downpour. Season 2 is average or varying rainfall or no continuous downpour. Or 3 is continuous downpour. So according to the rainfall characteristics and your catchment characteristics, you can choose this percentage, and you can simply calculate how much may be the runoff in these small watersheds in the Uttar Pradesh region. Similarly, Strange table. So Strange studied the available data on rainfall and runoff in the border areas of present-day Maharashtra and Karnataka, and obtained the value of runoff coefficient as a function of catchment characteristics. So this is the Ks is the coefficient, and R is your runoff, and P is your precipitation. So this for this K, for the purpose of calculating yield from the total monsoon rainfall, the catchments were characterized as good, average, and bad by the Strange. So this is how the good catchment, average catchment, bad catchment. If your rainfall is this much, you can take this Ks value from this table, lookup table, and you can estimate the how much runoff can be generated if this kind of rainfall is occurring in the watersheds in the Maharashtra border of Maharashtra and the Karnataka. So these are the empirical approaches. Similarly, some other Igneous and D'Souza formula, Khosla formula, they have been developed for this specific region, relating the runoff with the precipitation only. So based on the previous observations, they have developed these models. So these are all the examples of empirical methods for rainfall runoff modeling. Now, known as Soil Conservation Services curve number model. So this model was developed by the Soil Conservation Services Department, which is in USDA, United States Department of Agriculture. So there is one small department. They have developed this model. So the name of the model is SCS curve number. The name of this department, Soil Conservation Services, has changed to Natural Resource Conservation Services. So name of the model has also changed from SCS to NRCS method. So you should not get confused between these two, SCS or NRCS. Both of them are same, or some people also called it as a curve number method, hydrologic soil complex number method. So all of them are same. So you should not get confused. So in SCS method, it is assumed that for a given rainfall, the ratio of actual infiltration to the maximum possible infiltration is equal to the ratio of actual runoff to the maximum possible runoff. So it is a conceptual model where it has been assumed that the actual infiltration, the ratio of actual infiltration to the maximum infiltration is the ratio is equal to the ratio of actual runoff to the maximum possible runoff. So if I what is actual infiltration? Actual infiltration is how much is coming as precipitation, how much is the initial losses, initial abstraction, and how much is the actual runoff. If I minus the initial abstraction and the runoff, actual runoff from the precipitation, it will give us value of actual infiltration. Similarly, when it will be the maximum runoff, possible runoff, when if we consider that our soil is saturated and there is no infiltration, then in that case only some initial losses may happen in terms of evapotranspiration. So P minus IA. So if I take this precipitation minus only the initial losses, if there is no infiltration, then there will be maximum runoff. So if I rearrange this and considering that the initial abstraction is equal to zero point 0.2 of maximum possible infiltration, the equation for the runoff becomes this: precipitation minus zero point 0.2 multiplied by maximum possible infiltration whole to the power square, and then P plus 0.8 of S. So now precipitation you can get from the rain gauge or from the remote sensing data. If you have the rainfall data, you can estimate the runoff if you know the maximum possible infiltration, that is S. For S, it is defined as S is equal to 25400 divided by curve number minus 254. It is in mm. So now this the Q is dependent on P and S, where P is known but S is unknown. For now for S, this is the formula where Cn is the unknown. This Cn is the nothing else, it is curve number. So this curve number, it is a function of your soil and the vegetation class of the watershed and the incident moisture condition. So if you know these three, you can get the curve number. So what the researchers at Soil Conservation Services, what they have done, they have analyzed small agriculture plots in USA, and they have estimated this curve number, and then how much is the so in this method, the soil has been grouped in four classes: A, B, C, D, based on their runoff potential and the depth. So lowest runoff potential soils are grouped as A, whereas highest runoff potential soils are grouped as B. So in between class of runoff potential, they are classified as B and C. Then this is the lookup table provided by the SCS or the NRCS. So if your land use is like this and your soil is either A, B or C or D, your curve number may be these values. So if you have the land use and if you have the soil map, you can use this lookup table to get the curve number values. Okay, if you know the land use and soil, and then you convert that soil into the soil hydrologic group, and then you can get the curve number values from this lookup table. But these values are corresponding to incident moisture condition 2. So what is incident moisture condition? So incident moisture condition tells that the cumulative of previous 5-day rainfall, if it is less than 12.7 mm in the dormant season, it belongs to incident moisture condition 1, and if it is less than 335.6 in the growing season, again it comes under the AMC condition 1. Whereas the if the cumulative of previous 5-day rainfall is 12.7 to 27.9 mm in dormant, or 35.6 to 53.3 in growing season, then it is under the AMC condition 2, and then if it is more than 27.9 or 53.3, then it is AMC condition 3. So this is why this is required. This is required because it will tell us about the condition of soil. If in the previous 5 days, if some rainfall has occurred, then soil may be saturated to certain extent. So accordingly, with the help of this, we can define the incident moisture condition. Now, as we have seen that the lookup table provided by SCS was corresponding to an incident moisture condition 2. And then in the all of you know that rainfall, it varies spatially and temporally. So if there is a special variation of the rainfall, if some rainfall is occurring here and somewhere it is not happening, then the ANC condition may change. It will not necessarily that your entire watershed on a particular day it is under the AMC condition 2. So if we analyze the rainfall data, we can identify the conditions, AMC conditions throughout the watershed, whether it is 1, 2, or 3. If in our study area the AMC condition rather other than 2 are satisfying, then we have to convert the CN2 values. Those are provided here in the lookup table corresponding to AMC condition 2. We have to convert them for the AMC condition 1 and AMC condition 3. So in literature, the conversion from CN2 to CN1 or either CN3 are provided, and you can choose any of these method to convert the AMC, the CN2 value to either CN1 or CN3, that is column number 1 or column number 3 or column number 2. Now, as I told you earlier, the method was developed for the small agriculture plots. So in the agriculture plots, the slope was less than 10%. So it is not necessary within a watershed your slope will be less than always it will be less than 10%. It may be more than 10%. So later on, improvements have been done to incorporate the slope. So alpha is your slope in percent, and you can first you have to correct the term number for slope and then for the AMC condition, and then whatever you will get, that will be your final CN map. So once you will get the CN, and you can calculate the S, and we have seen that in the formula the IA has been taken as 0.2S. For if your condition AMC one condition is satisfying in USA, generally IA has been taken as 0.3S, and if condition 3 is satisfying, the IA has been taken as 0.1S. So accordingly, we can also change the this assumption of initial abstraction either 0.1, 2, or 3 according to the AMC condition. So in India, the watershed surveyed by in India, it is reported that for black soils region with AMC 2 and 3, we can use initial abstraction is equal to 0.1 of the maximum possible retention. Black soils region with AMC condition 1, we can use 0.3S. For all other regions, we can also use IA is equal to 0.3S. Here I have shown you the flow chart to elaborate how remote sensing data can be used in this method. So earlier this method was developed for small agriculture plots where the soil was consistent and the land use was agriculture, but in a watershed it may vary. So now considering the as the remote sensing data, the satellite data which we may use to generate the land use land cover, we can generate it in a raster format, that is the regular grid. So one grid of that data may be considered as the one of the plot, and we can do that this kind of analysis for each and every pixel in a remote sensing data, and we can estimate the runoff potential of that particular piece of land. So in the remote sensing data, if you have the remote sensing data, if you have multispectral remote sensing data, you can generate the land use land cover map. And if you have the stereo pair data or the using the SAR data using DINSAR, the INSAR technique, you can generate the digital elevation model. So if you have the land use land cover map, and if you have the soil map in GIS, after crossing, you can convert the soil map into the hydrological soil group A, B, C, D. You can, knowing the soil characteristics, you can convert that into hydrological soil group, either A, B, C, or D, and then If you cross these two maps, land use land cover map and hydrological soil group map, you can generate the curve number 2 map using the lookup table provided by the SCS. Okay. Now, if you have the DM, you can convert it into slope, percent slope map, and then you can do it the correction for the slope. And if you have the rainfall data, you can analyze your rainfall data and you can identify the AMC condition. Now, knowing the AMC condition, I will convert the CN2 into CN1, CN2 or CN3. Once I will identify the AMC condition and convert the CN values, I will get the final CN map. So using that final CN map, I can calculate the S, and then knowing the S, putting into this formula, I can calculate the runoff. So this is the crux of the application of remote sensing GIS in SCS method. So I will I can understand that it is difficult to understand this. So I will show you one case study we have done on Solani watershed, which is in Uttarakhand and partly in Uttar Pradesh. So this is the location of Solani watershed. It as shown on LS3 image of October 2006, and you can see that elevation varies from 200 to 800 meter, and the area of the watershed is around 529 kilometers square. Okay. And then we have used the meteorological data for the monsoon season of 2006 from the AWS installed by the IIRS itself. And for the land use land cover mapping, we have used the Indian remote sensing P6 list 3 satellite image for the 10th October 2006. And we have used the SRTM DM for the topography or the slope. And for soil information, we have taken from the soil types from the Agriculture and Soil Department of IIRS. Then initially we have pre-processed the DM to delineate the watershed, Solani watershed. So that day also I have shown you this, that if you have the raw DM, do the fill sink correction, then flow direction, flow accumulation, then you extract the drainages, and then from the drainages you can generate the watershed boundary maps. And considering we have considered the outlet as at Roorkee, so this is the entire watershed boundary. Now, once we have the watershed boundary, we have clipped the remote sensing data, and we have done the classification, and we could generate this kind of land use land cover map, which is comprised of dense forest, sparse forest, fallow land, built up, perennial, river perennial, river seasonal, scrub, agriculture and agriculture plantation. So you can see here, this can be done. Then this is the soil map of the watershed, which is comprised of loomy sand, sandy loam, and sandy clay. Then we have done the field work to validate our land use land cover mapping, and this is the land use land cover map and soil texture map of the study area. And this is the coverage of the different classes identified on land use and the soil type, how much area they cover within a watershed. So using these two maps, land use land cover map and the soil type map, first we have converted this soil map into the HSG map, then knowing based on their characteristics, and then knowing the HSG and the land use cover at each pixel. This is the curve number 2 map. This curve number 2 map has been generated using the lookup table provided by SCS method. So now at each pixel, I know what is the CN value. Now from the DM, we have generated the percent slope map of the Solani watershed. Then using the slope adjustment, we have done the slope correction. So we have used both Shapley-Williams and Vaughan's approach for the slope correction. So this is the we're using a Shapley-Williams equation. This is the slope corrected CN2 value, and this is the using the Vaughan's approach. slope corrected CN values. Now what we have, as we were not having the observed data, what we have done, we have we have extracted the curve numbers for each of the 34 sub-watershed. There are 34 sub-watershed within the Solani watershed. So for each sub-watershed, what is the curve number without any slope correction? With using slope correction using the Shapley-Williams, slope correction using the Huang's approach. For each 34 sub-watershed, we have extracted these values. And then for each sub-watershed, we have analyzed the rainfall data. And then we have used Shobanian and Hawkins methods to convert the CN2 value to CN1 or CN3 based on the AMC condition identified. So these are the CN1 and CN3 maps of the watershed. So this is the CN1. If CN1 condition satisfied in a watershed, this is the CN1 value. We're using this Shapley-Williams slope correction approach, and this is when you are using the Huang's approach. This is the if AMC condition 3 satisfying in the watershed. This is the curve number correspond to AMC condition 3 using the Shapley-Williams slope correction, and this is similarly using the Huang's slope correction approach. This is the rainfall maps, seasonal rainfall map and the annual rainfall map of the study area. We were having daily rainfall data, and based on that we have extracted the AMC condition. This is for just to show the variation in the rainfall. I have shown these figures, and then in each sub-watershed, how much percent of the rainfall is the runoff. It has been identified without any slope correction in within each sub-watershed, how much percent of the rainfall is the runoff. Using the Shapley-Williams slope correction, how much is the percent of the rainfall is the runoff, and seasonal runoff within a season, how much is the runoff as the percentage of the rainfall using the Huang's approach. So this is annual. Earlier it was signal study. This is an annual time scale. How much is the rainfall percent is runoff without any slope correction using Shapley-Williams, slope correction using Huang's approach. So if you can see here that the annual rainfall of the watershed is 800 something, and without any slope correction, the runoff is 80. After slope correction using Shapley-Williams approach, it is 78.75, and using Huang's approach, it is 80.88. In seasonal time scale, this is the rainfall in a watershed. Without any slope correction, the runoff is around 80.91. With using the Shapley-Williams slope correction, it is 78.75 mm, and using the Huang's slope correction, it is 80.86 mm. So this is for entire sub-watershed, and this is for all the sub-watershed. How much variation is there from rainfall? How much it is varying from which value to which value, and then how much is the runoff variation is there. So this is just to show you the potential of remote sensing and GIS in estimating the runoff using the SCS method. So at each pixel, now you can estimate how much is the runoff potential or how much is the runoff depth. So this is at each watershed, how much is the rainfall and how much is the runoff is there in each watershed. So this is how the for each sub watershed, how much is the rainfall and how much is the runoff. It has been tabulated. So why we have to study the SCS curve number method? Because if you are using the soil water assessment tool, that is SWOT, which is most widely used hydrological model these days, in the background it also uses the SCS method to estimate the runoff. Okay, so that is why we should understand in the background how the runoff has been calculated. So in the SWOT, in the background, SCS method has been used to calculate the runoff. Similarly, if you see, if you are using the Hack HMS model for rainfall runoff modeling for a storm, again, it is for this. This is the methodology of HMS. If you see, you need DM for hydroprocessing, then you will get the drainage area map and the drainage map and the watershed maps or watershed maps. If you have the land use maps, if you have the soil map, you can integrate the data. And for runoff calculation, again in the background, there are different type of models, methods we can use to estimate the runoff. Which and out of them, one of them is your SCS curve number method. So you can see here in the loss methods also, you require the SCS curve number, and for runoff calculation also you require the SCS method. So these are the other methods. There are other methods as well, and for the runoff calculation also there are other methods, but you can also use the SCS method. If you see in most of the studies using the HMS, they have used only the SCS method for both loss and the runoff estimation. The next, we have seen the empirical models. We have seen the conceptual model, that is SCS curve number method. Now I will focus on the physically based hydrological model, that is variable infiltration capacity model. So what are the advantages of VIC model? VIC has played multiple roles as both hydrologic model and the land surface model. So it is land surface scheme as well. So as a semi-distributed micro-scale hydrological model, it balances both the water and the energy budgets within a grid, and it captures the subgrid variation as well. So how it what are the distinguished characteristics of the VIC model? Subgrid variability in the land surface vegetation class. I will tell you how it consider the subgrid variability. Subgrid variability in soil moisture storage capacity. Drainage from the lower soil moisture zone, that is base flow, as a non-linear. If you have studied hydrology, you may be knowing that most of the hydrological models, they consider base flow as linear. However, it is a non-linear process. So in this method only, the base flow has been considered as a non-linear recession. So and it includes the topography that allows for orographic precipitation and temperature lapse rate, resulting in more realistic hydrology in mountainous regions. If you are studying the hydrology of mountainous watersheds or basins, then this may be the one of the best model to estimate the runoff with higher accuracy. So to simulate the stream flow, VIC results are typically post-processed with a separate routing model, which is developed by Lohmann et al. And based on the linear transfer function to simulate the stream flow. So VIC has adapted to allow implementation of water management effects. So you can including the reservoir operation and irrigation diversion and return flows. It also incorporates the lake storage effects to estimate the runoff at the outlet. So this is the, as I told you, the model, it works on the grid scale and the grid level. So this is one of the typical grid of a your basin or study area. Okay, so within this grid, the model will estimate the evaporation, evaporation from the canopy, long-going radiation, short wave radiation, and then if you know the precipitation, then it considers the different vegetation layers, different soil layers. So these are the 3 different soil layers. So it calculates the runoff and the base flow. So it calculates the runoff based on the variable infiltration curve. So that is nonlinear function, and all of you understand this, that this is the variable infiltration curve. So it is a nonlinear curve. So up to certain level, there will not be any runoff because all the water will go into the soil. And once the soil will be saturated, then only the runoff generation will start. Okay, so this is the equation for the variable infiltration. And if you see here, the base flow, how it is Arnaud's method it uses at the background. So up to certain limit of the soil moisture or the low soil moisture level, it is linear. And then once the soil moisture of the third soil layer increases, the base flow increases as a non-linear recession. Now, how it calculates the subgrid availability, how it considers the subgrid availability. So this is one of the grid of around, suppose if it is 3 kilometer by 3 kilometer grid. So within a 3 kilometer by 3 kilometer, your land use or land cover may be different. So for each land use land cover class, it will calculate the water balance. Okay. So suppose one is your forest, two is your forest, one is agriculture, and this class is urban, this is bare soil, and some the n plus one is your bare soil, and this is some other class. So for each class, it will do the water balancing, and then for a grid, statistically, it will tell you how much is the water balance. So this is how it considers the subgrid variability in precipitation in the vegetation class. Similarly, soil moisture storage, because the soil moisture storage of each of the land use class will be different, and similarly infiltration may also be different for each of the land use land cover class. So knowing the land use land cover class, it is dividing the base the particular grid into the different um, fractions based on the your land use land cover class, and then it is considering the subgridability and in infiltration, soil moisture, and vegetation. Now, precipitation. If your study area is mountainous watershed, then you have to define the elevation bands for each elevation. How much mean area is lying within a for a mean elevation the classes land use classes are lying within that elevation band, then it calculates the runoff. And if as the elevation changes within this 3 kilometer of the grid, then the precipitation value, it will automatically convert the precipitation into rainfall and the snowfall. So as the temperature, we have to define the temperature, in up to what temperature snowfall may happen, and up to what temperature rainfall may happen. If you define that criteria, it will automatically convert the total precipitation into either rainfall and the snowfall. Okay, and then it can be used. So this is how the orographic effects can be incorporated in the big model for the rainfall runoff modeling. Okay, so you can run this model into water balance mode. If you have only the in your meteorological data, if you have only the temperature, minimum temperature, maximum temperature, and rainfall, you can run it into in at daily time scale. Then you can run it at in water balance mode. If you have the rainfall, temperature, minimum temperature, maximum temperature, mean temperature at sub daily scale, then you can run it into full energy balance mode. If you can also run it in frozen soil, and some other special cases also can be incorporated in the weight model. So in the background, as it is a physically based model, how it calculates the total evapotranspiration. So your total evapotranspiration is the sum of sum of the particular land use land cover class. If there are n classes, then this is the coverage of each class. How much is the evaporation from the canopy from that particular land use class, and how much is the transpiration from that particular class, and how much is the evaporation from the bare soil, multiplied by this is the fraction of the bare, this is the C, n plus in the bare soil, and even is the evaporation from the bare soil. So here the EC, that how much is the canopy evaporation. Canopy evaporation depends on the your maximum amount of water that canopy can intercept, that is IM, and your evaporation, and the architectural resistance, and the aerodynamic resistance to the evaporation. So if you know these values, you can calculate the canopy from the canopy evaporation. And for evapotranspiration, that EP, it is using the Penman-Montel method in the background, where the lambda V is the latent heat of vaporization, Rn is the net radiation, G is the soil heat flux, and Es minus Ea represents the vapor pressure deficit of the air in Pascal, and rho is the density of air at constant pressure. Cp is the specific heat of the air, and delta represents the slope of the saturation vapor pressure temperature relationship, and psychrometric constant is your rho. So in this way, it calculates the. This is the most widely used method for the evapotranspiration estimation. So this is how it calculates the evaporation from the canopy, and from the vegetation, transpiration is calculated again based on the how much it can intercept, leaves can intercept, and the how much is the evapotranspiration, and the what is the architectural resistance and the aerodynamic resistance. And for bare soil evaporation, that is E1, it is the evapotranspiration and the change in the soil moisture, the infiltration with time. If you integrate from the particular area, uh, then you can calculate the bare soil evaporation. So this is, if you know this, all the three: bare soil evaporation, vegetation transpiration, and canopy evapotranspiration. If you take the sum of all three, you will get the total evaporation. So that is what I am trying to convey. That total evaporation is the sum of the canopy evaporation, evapotranspiration from the vegetation, and the evaporation from the bare soil. Now, runoff and base flow, it is estimated using the Liang's method. That is the sum of surface discharge and the base flow. So it is a for each land use class. For each land use class, how much is the discharge and how much is the base flow. And if you take the sum for each of the land use class, then it will become the total runoff of the that particular grid. So this is how the surface discharge and the base flow has been estimated in the method based on their porosity of the soil and the depth of the soil, second layer, depth of the second layer, and the precipitation in the grid, depth, soil depth of the second layer, and the volumetric soil moisture of the grid grid, and the second layer. So based, if you know all these, or you can calculate the runoff from the surface and the base flow. The base flow, it is estimated using the IIRS method model, which is defined in this particular reference. So all of you know, I have shown you that up to certain threshold, it is linear, and after this threshold of the soil moisture, it is nonlinear. So this is how the base flow has been estimated in the background. So for running this model, we have to generate certain files, input files, such as soil parameter file, which describes the unique soil properties for each grid cell with respect to each soil layer, and mean rainfall and the elevation data. In the vegetation library file, you have to define the parameters of different vegetative types and their variation with respect to time. So here we are giving the how the vegetation characteristics or properties changes with time. So temporal information we are providing in the vegetation library. Whereas in the vegetation parameter file, we are providing the vegetative composition of each grid cell as well as the root zone characteristics. So within a grid, what kind of land use are present, that we are defining in the vegetation parameter file. Whereas in the vegetation library file, how the different parameters of vegetation, such as architectural resistance, aerodynamic resistance, the displacement, albedo, so for that, how they are varying with time throughout the year. that we are defining in the vegetation library file. Whereas in the forcing file, we are defining the meteorological data, which are rainfall, minimum and maximum temperature, or if you have the wind speed, cloud cover, sunshine hour, so those can also be incorporated in the forcing file. So how we implement the model? So conducting the for conducting the hydrologic studies, simulate the ensemble of stream flow and hydrologic variables for forecast purpose, reconstructing, analyzing drought events, and for the water management. So I'll show you. I can understand that understanding this kind of complex model in 1 hour time, it is really difficult. So I have shown you that so many input files we have to generate. I will show you how these files can be generated with the help of this case study. So this is we have done one study on the impact of land use and cover change on hydrology of a watershed of a basin. So I'll show you with the help of the study how we have set up the model. So the main objective was to set up the regional scale semi-distributed hydrological model in Pennar Basin, and then we have studied how this hydrology has changed from year 1985 to 1995, then 1995 to 2005, and then how the land use has changed between these 3 years and 3 decades, then how the hydrology has changed based on the change in the LULC. So this is the study area. This is the Pennar plus other river basins in the Pennar region, river basin. So those have been considered in this analysis. And then the entire basin, it has been discretized in 25 by 25 kilometer grid. So you can see here the how the entire area has been discretized in regular grids. So now the grids falling within my river basin boundary, those are the active grids which I have to run in the model, and I have to estimate the runoff. So I have so this basin is consists of Musi, Pennar, and Punya rivers, and the average annual rainfall of the basin is around 900 ml, and average temperature of basin varies from 18 degree centigrade to 14 degrees 40 degrees centigrade. Okay, and the average annual rainfall in 1995 was 1894, and average rainfall in the 2005 was 2798 ml. For model setup, we have used the GTopo Hydro 1K DEM, which is available at this source. And for land use land cover map, we have used the ISRO GBP land use land cover map available for 1995 and 2005. And the vegetation parameters, which we define in the vegetation library file, we have taken from the land data assimilation system of the NASA, which is available at particular source. And for soil, we have taken the NBSS LUP, that is National Bureau of Soil Survey and Land Use Planning, which is in Nagpur. They have generated the land use the soil information, and for each of the basin in India, and soil texture and other properties they have provided in their reports. So, and then for daily rainfall, that is IMD graded data we have used, and for daily maximum and minimum temperature, we have again used the IMD graded data, which is available on the which is freely available on the IMD IITM Pune website. Now, how we have run the model, we have defined the area of the interest, then generated the land surface inputs files, that is vegetation library, vegetation parameter file from then soil parameter file. Then we have generated the meteorological file. Then we have downloaded, as this is the open source model. You can download, you can modify. So that model has been downloaded and compiled for the model for the big source code. And then the global parameter file, which control all the files, that all the input files, and run parameters. It has been generated, and then using this command, the model has been run. So this is how the soil parameter we have defined. So if you can see here, these many parameters we have to define in the soil parameter file. Whether, see, this is whether you have to run the that grid or not. So all the grids falling within a watershed or the basin, those we will give as one value, and other grids we will give as 0. And this is grid cell, means what is the grid cell number, their coordinates, lat long, and then this infiltration, variable infiltration curve parameter, fraction of ds max, where ds max is maximum velocity of base flow, and ws fraction of maximum soil moisture, and the depth. These are those are, I have highlighted in red color, are the calibration parameter of this model. Okay, so this you can vary. Then you have to define the hydraulic conductivity, you have to define the initial moisture, you have to define the average elevation of the grid, then bulk density of the soil particle density, so annual precipitation, residual soil moisture. So these you have to define in the soil parameter file, these many parameters. So how can I define all these parameters? For each soil type, we require these many inputs: bulk density, field capacity, wilting point, porosity, saturated hydraulic conductivity, and the slope of retention curve, that is B. If you have these using the pedo transfer functions, you can define all the parameters provided here or required in the soil parameter file. So you require pedo transfer functions to define all those parameters. So this is how you can define those the parameters in the soil parameter file. So this is the grid number, lat long of the center of the grid, then variable infiltration curve, fraction of ds max, maximum velocity of base flow, fraction of maximum soil moisture, and then this is K1, K set and K set 2. One is for soil layer 1, and for the second layer of the soil is K set 2. For each soil layer, you can run this model for number of soil layers. Generally, we are running this model for at least 3 layers of the soil. So for here, I have shown you the example of 2-layer wick model. So for each layer of soil, you have to define the K set, that is saturated hydraulic conductivity. Then you have to define the elevation, average elevation, and similarly you have to define, if it is a 2-layer soil, 2-layer wick model, you have to define around 36 parameters in the soil parameter file. So as I have told you that ds max, ws, bi, and the soil depth are the calibration parameters. Calibrate the model. If your output is not in concurrent to the observation, then you can slightly change the values of these parameters and you can calibrate your model. Whereas in vegetation parameter file, you have to define like this. These many information, that is grid cell number, vegetation type number. So you will give for each class of vegetation, you will give certain code, that is in numbers. So that number you have to define. Okay, how many classes are there in a cell and what are their class numbers? You have to define. You have to define the fraction of the grid cell covered by that particular land use land cover class, and then you have to define the routing depth. Okay, and the routing depth fraction for the current road zone. So these many parameters you have to define in the vegetation parameter file. So this routing depth is different from the soil depth. So there it is not same. So it tells about up to what depth of the soil the roots may go. So for evergreen forest, it may go up to 3rd layer of the soil, and for the grasses or agriculture crops, it may not go up to the 3rd layer. So that we have to define. This will help us to calculate the evapotranspiration. So these you have to define in the vegetation parameter file. So the grid, within a grid, how many land use classes are present, and for what are those classes present in the grid, what are their fractional cover within a grid, that you have to define in the vegetation library file. Whereas in the vegetation parameter file, then in vegetation library file, you have to define these many parameters. So what is a class, which class, land use class is there, whether the overstory is present, architectural resistance, stomatal resistance, LAI you have to define for all the months. Okay, why we have to define the LAI? Because LAI changes with the time. Okay, as the growing season starts, LAI will increase. As the dormant season starts, LAI will decrease. And then if the LAI is changing, means your interception will change. Then albedo, for all the 12 months, you have to define the albedo. Roughness, you have to define for all the 12 months. Displacement, you have to define for all the 12 months. And then wind, then you have to define the minimum incoming shortwave radiation. Then radiation attenuation, wind attenuation, trunk to total tree height ratio you have to define. So these many parameters you have to define. So if you see in India, most of these parameters are not measured regularly. So that is why we have taken the data from the land data assimilation system, as I have shown you earlier in the data used slide. So now how to define these parameters in the vegetation parameter file and the vegetation library file I have shown here. So this one is the grid number. First grid number, there are two types of land use land cover class, and these are their numbers, that class number 1 and class number 9 are present with their fraction of 0.64 and 0.36. So this sum should be 1 always. This sum of the fraction should be 1. All of you can understand this. And so this is grid number 1. There are two classes, and these are those two classes, and their coverage is this much percent within that grid. So this is how you have to define these parameters in the vegetation parameter file. And in the vegetation library file, if your land use classes are, these many land use classes are there, so this kind of information is available on land data assimilation system website of the NASA. For LAI, monthly LAI values are present, given. Albedo, monthly albedo is given. Monthly roughness you have to define. Monthly displacement you have to define. Wind above a certain height, and then radiation attenuation, wind attenuation. So this is how you have to define these parameters in the vegetation library file. So that is architectural resistance, LAI, albedo, monthly LAI, monthly roughness, vegetation displacement height, monthly you have to provide. All these parameter files, soil parameter file, vegetation parameter file, vegetation library file, all we have to generate in ASCII format for each of the grid. So in the when we have divided this or discretized this basin boundary in 25 kilometer by 25 kilometer grid, there were around 202 grids. So each grid we have to define the soil. For each 202 grids we have to define the soil and the vegetation library. For each grid we have to define, and for each grid we have to generate this meteorological forcing file on precipitation, maximum temperature and the minimum temperature. Then once all these files are generated, using the global parameter file, which controls the simulation, whatever the conditions you have you have defined in the global parameter file, and location of these parameter files, it will run the model. And if your study area lies in the snow-fed region, you have to define the elevation band file, as I told you earlier. So these many parameters you have to define in the elevation band file. If in your study area there are lakes, then you have to define certain bathymetric parameters, as they can store the water, and it can store the water, and your runoff may decrease. So these bathymetric parameters also you have to define in the vegetation in the lake parameter file. Now these are the results. So we are this is the land use map of 1985, 1995, and 2005. So we have these are the major changes in the land use. Evergreen forest has decreased, deciduous forest has decreased, cropland has decreased, whereas built up has increased from 1985 to 2005 by around 6%. So when the land use will change, definitely it will have some impact on the hydrology of the basin. So we have analyzed that there was not much change from 1985 to 95 in the runoff. However, as the built-up has increased in 2005, runoff has increased from 53 mm to around 76 mm. Then on the other components, if you see, the runoff has increased, base flow has increased, and evapotranspiration has increased by around 24% from 1985 to 2005. So this is how the models have been used, can be used to estimate, to study the impact of land use land cover change on the hydrology of the basin. Then again, we have routed the runoff at the outlet of Nellore, at the Nellore for the Pennar River only, and we have found that there is not much change. Only slight increase in the runoff at the outlet was estimated for the Pennar River. Then, as this model works on a grid basis, so we have done the water balance study of entire Indian landmass. So we for this study we have used the GTOPO 30 DM, which is available at 90-meter resolution. Sorry, 1 kilometer resolution, and then soil map from FAO we have taken, and the University of Maryland Department of Geography, that land use map has been used for the vegetation parameter file. So with the help of these two, we have generated the soil parameter file. Using this map, we have generated the vegetation parameter file and the vegetation library file, and we have found that throughout the analysis period, what is the water balance, how much is the rainfall, how much is the runoff, how much is the evapotranspiration, and how much is the base flow. So, as I told you, this model works on a grid scale. So, this kind of spatial maps on the water balance components can be generated. This is the rainfall in 95, rainfall in 2000, and rainfall in the 2005. And corresponding runoff in potential in 95, 2000, and 2005. And how much is the ET in 95, 2000, and 2005, and how much is the base flow. So, these kind of informations or the spatial maps or spatial information are very useful in better water resource management and the policy generation. Then we have validated our results with the values reported in CWC by the CWC, and you can see that our study is estimates are very close to the observed by the Central Water Commission for each of the river basin. Then one of the detailed study on land use land cover change on hydrology of Pennar River basin has been done. So again, this is the Pennar River. In this study, the basin was discretized in 5 by 5 kilometer grid. So this is this NBSS soil map, and this is the land use map of 95, 85, 95, and 2005. So you can see the change in the land use. So the land use change matrix has been generated, and it was found that there is a significant land use change from 85 to 95. Then the model was calibrated and validated for the observed discharge data. You can see here, and these are the those calibration parameters, their range, and these are the calibrated values. And then you can see that what is the change in on the hydrology of the basin. If you see the rainfall, as we were studying the impact of land use land cover change, so we have kept the rainfall constant for the entire analysis, and then only the vegetation parameters have been changed. Then we have found that from 1985 to 2005, there is not much change in the runoff at the basin scale. But if you see, at the hotspots areas of land use land cover change were identified. So this is the land use land cover change map, and these are the hotspot areas where the land use change has been taken place in the basin. And if you see here, then what we have done, we have analyzed the whether the change will increase the runoff or the land use change will decrease the runoff. So the red pixels show the these are the land use changes where the runoff may decrease, and the green where the changes are in green color. So this shows the runoff should increase. So if you see the area of change in the land use which will induce the runoff reduction is around 1087 kilometers square, and the changes in the land use which will induce the runoff increase again are around 1100 kilometers square. So if you see both of them are balancing the change in the land use. That is why we have not found much change in the runoff at the outlet, as I have shown you earlier. Then we have found the spatial changes, because at the basin scale it is difficult to analyze how much will be the impact of land use and cover change in the runoff. So we have analyzed the spatial change in the runoff. So this is the long-term climatic normal of basin runoff, ET and base flow. So this is from 1951 to 1984. We have run the model, and then we have generated this normal maps, average maps from 1951 to 84, and then we have identified the anomaly in the runoff and the if you are this is the runoff in the year 1985, 95, and 2005, and this is the anomaly. You can see that there are patches where the runoff has changed a lot. So this blue color, there are negative change, and in the red color or the orange color, they are showing that there is a positive. That means runoff has increased in these regions, and runoff has decreased in those regions. Surface runoff has decreased. Similarly, how ET has changed with time, and how the base flow has changed with time due to the land use land cover change. So you can see then certain analysis has been done that why it is happening, because what kind of conversion has taken place, why the runoff is increasing, why the runoff is decreasing. So we have analyzed those changes in the land use, and we have found that certain land use change will increase the runoff, and certain land use change will decrease the runoff. Then these models can be used for studying the impact of climate change on the river basin. So one of the case study we have done on the Krishna River Basin. So this is the study area, Krishna River Basin, which lies in Maharashtra, Karnataka, and Andhra Pradesh. We have used the this digital elevation model, and this is the drainage map of the Krishna River Basin. So this is the coverage of basin in each of these states. And these are the stations for which the data was available on IIRS portal, as I told you. For each station, for this time period, the data was available. That has been downloaded, and then the model has been this big model has been used to study the impact of climate change on the hydrology of this basin. So in this study, the basin was discretized in 25 by 25 kilometer grid. These were the inputs: SRTM-DM, land use land cover from ISRO GBP, soil map from the NBSS LUP, meteorological data we have taken from IMD, and discharge data from IIRS, boundary basin boundary from IIRS, and for future climate change, future climate data we have taken from the Codex. And in this study, we have only used the two scenarios, that is moderate scenario, that is RCP 4.5 and RCP 8.5. Then initially the model was calibrated and validated. So this is the pre-calibration results at this particular station, and this is the after the calibration. You can see that there is huge improvement after the calibration at this station. And then the model was validated at the outlet, which is at Vijayawada. So this is the validation result. Now our model, this has been done for the past data, which is from 1951 to 2018. It was available. So that data have been used, and model has been calibrated at different stations, as I mentioned earlier. And then that calibrated model has been used to study the impact of climate change on the hydrology of the basin. Initially, the change in the climatic variables has been analyzed. You can see here the in both the scenarios, 4.5 and the 8.5, it is showing that with the time the rainfall may increase, precipitation may increase in the region, and the minimum temperature is will also increase slightly, and maximum temperature is showing major increase in the uh, basin. Then it is simulated that the change in the climate, it will with the change in the climate, the runoff may increase in the basin. So within in both the scenarios 4.5 and 8.5, it was shown that the runoff may increase. If runoff may increases, so there may be the floods in the basin. So that we have analyzed hydrological extremes in terms of flood. It has been analyzed. So we have divided the study period into 2020 years time period. So within the time period, how many the events, such events may happen for the maximum discharge. So this discharge, with the help of frequency analysis, we have identified the magnitude, and this kind of magnitude, how many times this kind of events can happen, that we have identified. So in 4.5, you can see the number of these such events in each 2020 years time period, and in 8.5 you can see there are more number of such kind of events. So these kind of models may be useful to study the impact of land use and cover change, and impact of climate change on the hydrology of the basin. So these may help us to draw the policies, and for the climate change adaptation measures we can take based on the such analysis. So in conclusion, I'd like to say that there are a number of hydrological models available to study the rainfall runoff relationship. Each model requires certain inputs, and geospatial technology play a critical role in input generation for modeling. And then well-calibrated and validated models may further be used for assessing the impact of land use, land cover, and the climate change on the basin. So thank you so much